this workshop. It's been a great pleasure to meet friends and also listen to very exciting talks. So ideally, I would have wanted to talk about the work we have been doing on sampling from large language models, but so I wasn't able to do that. So I'm going to give a title that reads almost like the title of the workshop. So it's too general, so I decided to narrow it down. So I added this two today to this.
One of mine was really inventive.
Yeah.
This is upsetting me.
So I'm going to talk about some of the work that I've been thinking about over the past few years around fairness. And just I think a lot of people have talked about these problems. So I'm just going to give this example so this is now a classic example where you have a classifier, and then you basically try to look at how that classifier works for different subgroups here, white and African Americans. And then you see all of a sudden that the false positive rates of the classifier is hugely different for these subgroups. And so that's something that's very undesirable in practice. And so that's something that we really want to be able to address. And we want to be able to address these in, again, classification problems that get deployed in practice. And so there are a lot of practical challenges around actually getting any solution into these kinds of classifiers. And so this was an extreme example, but these kinds of issues appear everywhere. So you're solving a PCA problem, and then you'll start looking at the performance of your PCA for male and female, then you see that there is a problem. You solve a federated learning problem, and then you start looking at test accuracy across your devices, and then all of a sudden you may be able to see that there are some of the devices that get extremely low accuracy. You look at other types of approach. There is clustering problem, there is meta learning problems, and then you solve the meta learning problem. On average, it seems to be working well, but then you start looking at the worst performing task, and then you see there is a huge discrepancy. And so we are interested in basically addressing these kinds of issues in practical setup. So there are many notions of fairness, and there is kind of no one-size-fits-all answer. So there is individual fairness, where basically very similar to privacy notions. So you would desire similar outcomes for similar individuals. Or there are group fairness notions where, so we were talking about whites and African Americans. So you have subgroups, and then you would want to have a similar aggregate performance. In this case, maybe loss, maybe accuracy, maybe false positive rates of your classifier to be similar for different subgroups. And that's basically what the focus of this work is. So there are many different ways of doing algorithmic fairness promoting approaches. So I'm citing two papers from Flavio from 2017 and the recent work that he talked about. So there is pre-processing, there is in-processing and post-processing. And so I'm going to argue for in-processing for two reasons. One is that in practice, when we have these classifiers, so what happens is that the data keeps changing. So you have this classifier that's going to be trained maybe every week, but every week it's going to be trained on a new data. And so you basically capture the data, and then you want to basically run the classification, and everything has to basically run in an automated manner. So the lesser the moving parts, the easier. So when you have an in-processing model, basically you just capture the data, you run the training, you get the model and deploy it. Whereas now if you have two different things that need to run, it just creates more opportunities for things to go wrong. And from an information theoretic point of view, I'm going to argue that the in-processing is probably going to dominate the other two. So there is opportunities for loss of information for both pre-processing and post-processing method. So I'm going to focus on in-processing methods in this work. Okay, so that brings us to the first paper that I'm going to talk about. So it's relatively older in machine learning years, tilted empirical risk minimization from ICLR 2021. So the work was led by Tian Li, who is a PhD student at CMU, is about to graduate in collaboration with Maziar Sanjobi and Virginia Smith. And extended version of this paper is actually going to appear in JMLR this year. So what is empirical risk minimization? So in empirical risk minimization, the goal is we have an empirical loss. So that could be cross entropy loss. It could be an L2 loss. And then we average out that loss over our samples and then try to minimize that. So here we're solving a linear regression problem, which is basically an empirical risk minimization problem with an L2 loss or mean square loss. And that's the fit that we're getting. So is that a good fit? So a lot of people may argue that no, this is not a great fit because so we seem to see as kind of a structure underlying pattern for this data that we're not kind of capturing here. And what this paper is all about is basically just captured in one slide here. So we replace the empirical loss with what we call the tilted empirical loss. So what we're doing is that we're exponentially tilting the individual losses, and then we're taking the empirical average, and we are properly scaling it back to have basically some nice properties of whatever loss function that we had. And then what happens here is that if we have a positive t, we're going to end up highlighting these outliers that we had here. And if we have a negative t, this is going to start suppressing the effect of those outliers. And so we're going to, in effect, get some fairness properties for positive t's and some robustness properties for negative t's. Now, this is, so if you look at this, basically, this is, so if we look at the loss function, our loss functions are usually at negative log likelihood. And then, so what we are doing here is, in effect, we are looking at the scaled cumulant generating function of information, which is the negative log likelihood function. Now, there are many other ways of dealing with these losses. So I think there is great work by Mario, Peter, and Lalita about alpha losses that try to kind of, again, have some tunable way of calibrating classification. In here, we are, so this is an information theory workshop, so we are going to look at something that is information theoretically motivated. So for the rest of this part of the talk, I'm going to try to talk about some of the properties of this this objective, and then we will see some empirical results.
But this is also known as risk-sensitive optimization.
Yes, in classical strategies.
And classical statistics.
Yes. Okay, so what are some of these properties of the term objective? So it basically, so it traverses between mean loss to average loss to max loss as we send t from negative infinity all the way to positive infinity. So, and then it's kind of in a, varies between them in a smooth manner. Now, if you have a smooth loss function, so you will end up with a smooth objective still. If you have your loss functions are convex here, so we have like, so I'm giving an example with 3 loss functions that are quadratic. So you will end up with a convex objective for positive t, but as you can see, that the objective becomes non-convex for negative t. And so here are kind of the solutions, the minimizers of these objectives, so that minimizers are not unique. So under some assumptions, we can assume that you will end up in a parametric curve that you will be able to traverse the solutions. And so here, so it's a one-dimensional example. Here is our median loss. So this is the median of these three functions, which is, as you can see, it's both non-convex and it's non-smooth. And if you wanted to minimize that, it's a very hard problem to solve in general. And so here, so all of a sudden, one of the solutions of this term objective is capturing that, but that's more generally even in higher dimensional problems. The term could be related to these quantile losses, and we will come back to that. So this objective is basically could also be rewritten as a Rayleigh cross entropy between the uniform distribution and this W distribution. So what's this W distribution is basically it's our tilted loss for each individual kind of data point, which are normalized. Okay, and it could be also so. Let's talk about this W function a little bit more. So this W function is what we call empirical mismatched tilted postulated distribution. So basically that so F, remember, that's just the negative log likelihood. So this is just, so for t, t is equal to 1, that's kind of the gets back the postulated distribution. And in essence, what this is trying to estimate is this quantity here, where now I'm looking at the postulated distribution, but I'm multiplying it by P of X, which is the distribution that the data was generated from. And then I'm normalizing it appropriately. And we had come across these kinds of tilted distributions in earlier work in the context of looking at mismatched guesswork. So the guessing problem where now you are trying to do guesswork, but then the distribution, basically you're ordering your sequences from most likely to least likely according to a mismatched distribution. And then you would want to understand the moments of guesswork, and these quantities actually appear in those problems as well. I think Lalita and Oliver have like a great paper on that source coding problem as well. Okay, so again, there are other connections to regularization of the empirical risk, and it actually, so later we realized that it's actually a distributionally robust optimization problem with a KL ball that it's basically as well. So it's basically related to a lot of the literature around machine learning.
So D is your standard KL. H is.
That's present. So it's written in a little bit of a weird manner because so.
Okay.
Yeah. Okay. So now, how do you solve for this objective? So this is the objective that we have, and then we want to take its gradient, and then if we take the gradient, we will see that it's basically just the weighted sum of the individual gradients, and the weights are actually given by the W function that we just saw. So it's basically if you have a batch problem, so you would just compute these and then you take the gradient. But Usually that's not the case, and we end up needing to solve these things in using mini batches, because that's how optimization works at scale. Oops. I don't know why this thing appeared later, but so there is a stochastic solver for this problem. So the stochastic solver, the way it works is that every time you take a mini batch of the data, and then you compute the tilted loss. And now this tilted loss that you compute is basically, we will need to be able to keep track of, so this RT is the objective. So we need to actually try to keep track of the objective, because that's our normalizing factor. And in order to keep track of the objective, the proposal here is to actually do a tilted average of the previous steps. Basically, it's just the dynamics that keeps track of the previous step and what our current estimate is. And then we normalize the weights accordingly, and then so that we use that to update the parameters over this mini batch. And it turns out that we can get convergence guarantees for this algorithm. So the convergence guarantees have really bad scaling with t, so they have exponential scaling, which is, but that's not what we see in practice. But I think it's an artifact of the analysis. Okay, so I'm going to talk about some of the applications of basically this tilted empirical risk minimization. We applied it to a variety of problems involving fairness, also robustness for negative t's. I'm going to come back to that. And then you could actually mix and match fairness and robustness in different senses as well. So the first problem is a fair federated learning problem. As you can see, so the federated averaging algorithm left some of these devices with accuracies that were extremely small, and then you could actually apply the term algorithm, and then with almost no loss on the average performance, you get a lot smaller standard deviation across these devices, and then the worst case performance all of a sudden improves dramatically. You could apply it to the PCA problem as well. So it's basically work that specifically try to address PCA, and so here we are just taking the PCA loss, and then we're just trying to make them equal across the two groups using the term objective. You could use it for handling representation bias or class imbalance. Again, these are methods that specifically designed for class imbalance, so we just applied it out of the box here. Yes?
How big of a sweep do you need to, sorry, is T is a hyperparameter that you tune? How big of a sweep, or like how do you know what range to look over?
Yeah, so that's a good question. So for all of these applications, we swap T basically between 0.1 and 10, and in basically just 5 values. And we did, so we used, so in some cases, you may have a validation set that may have, may be unbiased, etc. So and that's basically what we're doing. So we're optimizing T on the validations.
But like in some of your plots, T is going, it looks like T is like 100 here. And
so, yeah, so in this one, we just, so if we send T to infinity, you virtually get minimax objectives back. And so here, the baseline method was a minimax method. We just wanted to show that you could virtually get the minimax method's performance back with a large enough t, but it's actually much faster to run this algorithm compared to the min-max optimizer. So here is another example that I think is actually very, very interesting. So this is a meta learning problem. So you have a multitude of tasks, and this is the objective that we wanted to solve. And then so it basically is a model agnostic meta learning method that solves the problem, gets a mean squared error of 1.23 on all the tasks, and then you see that some of like the worst case tasks get a really, really bad performance, and so worst 10% is like 5, and there is a big standard deviation. By applying term, what happens is that even the mean improves. So not only the worst case performance improves, but also we get an improvement on the average performance. So that's impossible if you're only thinking about the kind of the performance on the training data. So this just shows that we get models that generalize better, because this is what we are looking at here is the tests mean squared error. Okay, so there is follow-up work on semantic segmentation. I think I can skip this. And so come back to this question of, now can we use this objective to bound value at risk? So we know that we basically, so this looks like Chernoff bounds, and we know how to use Chernoff bounds to bound the tail distributions. And so the question is, can we actually develop something similar here? So what is value at risk? So value at risk, so we are looking at the losses that are larger than some gamma, and then we want to find the minimum gamma for which the quantile is smaller than alpha. That's what we're going to call VAR 1 minus alpha. And so this is desirable in many applications. Sometimes we want to, for example, optimize for 90th percentile, but these quantile losses are very non-linear, very non-smooth and non-convex, so it's not possible to optimize them. So in practice, people have looked at what's called conditional value at risk. That's kind of a smooth upper bound on value at risk, and then you can actually do CVAR optimization, and so it's used in a variety of contexts. And the question that we had is that, can you actually come up with an upper bound on VAR using term? To do that, we first derive an improved Chernoff bound for non-negative random variables. So basically here is the statement of the result. So this is the vanilla Chernoff bound. And so what we have here is just the -1 when you have a non-negative random variable. So in essence, sometimes I've had this issue myself, where like you're dealing with non-negative random variables and you want to get concentration bounds around 0. Chernoff bounds are very loose, and but you will end up actually applying the Markov inequality, and that gives you like the desired results. And this recovers Markov inequality for t equals 0, and basically generalizes that. Another difference is that now you're doing the search over all t's, negative as well as positive, and so sometimes actually the negative t's are going to be the optimal t's for this bound. Now the proof is super simple. It's just basically applying Markov inequality to this quantity so now depending on whether t is positive or negative. So this is going to be positive or negative. So you apply it twice and get the better of the two bounds. And yeah, just wanted to show this Chernoff bound for two extremely simple examples here. The first one is a uniform 0-2 distribution. The second one is a truncated normal distribution. And so the red curve is the Chernoff bound. The green curve is the true complementary CDF. And now the other curve that we have here is actually so the improved Chernoff bound. And so Tian did a great job at visualizing the optimal value of T that gives you this bound. And you see that for these values, the optimal value of T is actually negative. So we use this to derive an upper bound on value at risk. And so this is the upper bound on the value at risk that we got through this method. So it looks a little complicated, but it's the derivation is pretty simple using this new improved Chernoff bound. What is important here is that when you get this, so there is this minimization over T, but then in the end of the day, when we want to optimize this upper bound, now we want to do another minimization over theta, and minimization over theta is going to be, so everything is kind of a constant here. And so doing the minimization over theta is as if we're solving the tilted empirical risk minimization problem. So the same solver could be used to kind of derive these bounds. And then given the theta, now you can actually do the minimization over T. How much time do I have?
All right, I think 35 is when you finish, so 2 minutes.
2 minutes, okay.
Huh? Yeah, you start a little.
Okay. So let me skip this. So I think I'm going to skip the negative T examples. Maybe just talk about one simple robust regression example here. The problem that we are trying to solve is a regression problem, but now we are either adding noisy labels or noisy features. And the fun part is that you can apply term with, so if you, with the negative T, here we have in all of the regression problem, robustness problems, we just chose T is equal to -2, which worked. You may be saying that that's cheating, so it probably is, and so we don't have a better way of kind of optimizing T, but it's, as you can see, it's like compared to methods specifically designed for regression, it actually works much better, especially in high noise regimes. Yes.
The loss itself can operate both on soft classifiers and I missed that one. I'm so sorry.
Yeah, so I think basically, so if you look at it, right, there is nothing that says that it has to be a classification problem. Yeah. So what we're doing is we're just taking whatever loss function that you had and we're tilting it, and then so it puts.
So you are using squared loss there for
there we are using a squared loss in the meta learning problem. We were using the meta learning loss in the PCA problem. That was a different loss. So it's basically any loss we could tilt it.
Okay.
So yeah, with that, I'm going to stop, and I think I should have changed the title to 1. So yeah.
Thank you so much. Give us a minute to ask questions. Really? Yes, there are 2 questions. Ahmad, Zen comes before N.
I'm confused by something simple, but if you look at the negative T, you're multiplying the f by a negative number, doesn't that make bad things better?
So the 1 over, so there is a 1 over t that takes care of that.
Oh, okay, that's negative, okay.
Okay, the one slide that is skipped, which was about C bar.
Uh-huh.
I wanted to know what that is.
Yeah.
Sorry.
You had your definition. It's all about C bar.
Conditional
Conditional value at risk.
Here.
Yeah.
So C bar is known to be an upper bound on value at risk. So this is not our work. But now we are deriving a different upper bound on value at risk through these tilted losses. So this is now so C bar, the optimization problem is different, right, from the normal empirical risk minimization. Here, the takeaway is that the optimization over theta is exactly this tilted empirical risk minimization. Now you have to do another optimization on T. We didn't really derive a kind of a good way of round robining the updates on theta and T, so that's kind of left open. But at least the optimization over theta is basically solving for this objective, which is basically term.
In the context of your talk, I'm going to say that C bar is used by some folks as a fairness measure.
Mhm.
Is that correct?
Yes.
And I still cannot wrap my head around it for some reason, but like, do you have results in the fairness context with T bar?
So basically T bar is nothing. So in the end of the day, you solve this problem, right? And then it's as if you're solving the tilted empirical risk minimization for a particular T. And so those are the kind of results that we showed. So in a sense, this just motivates the fact that you're as if you're optimizing for the 90th percentile rather than the average.
Okay. Thank you. You know,